check who just posted a message here on. Okay. Not this one. Oh, 927, okay. Good. So let's get started. First of all, for students that haven't checked the Discord server in a while, we posted some sample images that you can use for inspiration for your assignment. First one, so you want to do all three things: project the card, the coin, and the dice in order to turn that into a magic trick. So probably the second simplest approach would be with the card. So here we actually have big playing cards. You can also use smaller ones. Cut them out in the shape of a playing card, but have them completely white or any other pattern that you want. And then the magic trick would be that you show the card to the person, and then it's a Queen of Diamonds or something. Then you can snap your finger, the vision system will switch it to a King of Spades. Right? Now for the user, it should look as if the card has swapped. Right? And if you're really, really good, you can do that as a sleight of hand. But that takes years of practice, so for us it'll be easier to program the computer to do that. Okay. Now you can also do other kinds of tricks with that, like color changes, or what else could you do? You could ask the person, oh, here, shuffle the cards, you pull out your white card secretly from the bottom, then you put your hand on top, you say, okay, what card are you thinking about? And then if they say, oh, I thought about the 3 of hearts, then you move your hand, boom, here's the 3 of hearts. People are gonna go crazy. So try and think of some way to turn that into a magic trick, but the main technical aspects of it is to extract the card from the video, project the card into the video to replace it. The second one is using dice. So I don't actually know why, but in Taiwan they sell these dice that are actually blank on all sides except one. So they only have like a 1 and a 2 and a 3 and a 4 and a 5 and a 6. The other sides are all white. Now, they must play some game. I don't know if they are used for mahjong or something. If you use those kind of dice for mahjong, I've just never seen them before. But for us it works. So now here, the same problem, right? You want to project now onto a 3-dimensional object. The card is easier because it's planar, right? It's just a single plane. The dice is more complicated because from most angles you'll be able to see 3 planes. So you need to think about the rotation and translation of that cube. In a sense, so it's also easier because the thing is smaller, so the details aren't quite so easily apparent. And lastly, we have the coins. So we have some plastic coins that you want to be able to place into. This one is the easiest one, right? Because you simply need to put the coins onto different parts of the playing field, make them appear or disappear, but they won't actually be handled by the user in most cases. So then you have the coins, you can move your hand across and snap your fingers, and then the coins are going to go to some other places. Just like in that video that magician did for America Got Talent. So I think the coins one is probably the easiest one to implement. Also, last time we talked about then what will it track? I just implemented a React application to do the color tracking with the standard color predicate that I often use, which is it doesn't find OBS. It doesn't allow me to switch to the OBS camera. No. Because I used the camera here already. Oh, it's okay, I can also do it on the phone. Okay, so here you can play around with that app with a color predicate. So you can see how tricky it is, so susceptible. So I'll get you can hold up the milk box. And let me just you have an iPhone, try it, because I'm not sure if it works on the iPhone. I think it doesn't. So then anyway, you can see, we can track the box. Yeah. Or blue or any other color you calibrate for. And it shows you the color predicates for red, green, and blue channel, as well as the difference channels, red minus green, red minus blue, and you can see the difference. If you don't have the difference channels, it becomes very difficult to track. And now if you move around with your box, then, yeah, okay, there, so bring it back to the other side. Yeah, so there it's, I can select a couple more pixels to make it more accurate. And of course, once you do that, then you start adding in false positives as well. And this should work on anything with the modern browser. Now, if you're interested in the code, I guess that's this one. Okay, I don't know how to delete that repository. It's this one. That is the correct one, and what's kind of interesting, here's the actual color detector. Uses OpenCV matrix multiplication, so it's implemented in WebASM, which means that those matrix operations are running at basically native speed. It's very efficient. If you were to do that using your own for loops, then it would significantly increase the load on your processor. But just if you have never done any React programming, web front end kind of stuff, then React is sort of the framework to use at the moment. 3 months from now, it'll be probably something else because they always come out with new frameworks. But if you look at the way that it started, then your React components actually, that makes sense if you are a C++ or a Java programmer or a Python programmer. You have a class, right? You have inheritance, you have instance methods, all that seemed reasonable. You have constructors, you can encapsulate state, data within your class. That's all nice and everything. And then you can have different instance methods, and also the life cycle of those objects would be pretty standard. Like when you call the constructor, that's when the memory gets allocated. When the destructor is called by either the garbage collector or yourself, then the memory gets freed. Variables lifetime is going to be dependent on that. Now, for modern applications, that's a little bit for complex user interfaces. Classes don't match quite so well because there's lots of things that could be going on in your application. So if you click and you delete an object, then like if you have a list of cars here and you delete one, then that needs to be updated throughout the entire application. That is often done using a publish-subscribe design pattern. Admittedly, Qt came up, has a nice solution for that using signals and slots, so I like those. But this also would work. But now the new style, this is now deprecated. So you can still write programs like that, but it will not be possible to do that in the future. The new style is to use functional components. So now, instead of having a class, you don't have a class anymore. You have functions. And okay, this is a function, right? This is what I understand under a function. 30 years of programming have taught me that. You have a function, it does one thing, makes some change to the state of your program. You have input and output parameters and things like that. And it goes to town and just do the processing. You can apply some local variables, all fine and good. But if you now do this in React, you have these functional components which are also just a function, but it's actually way more than that, because the function that I have here, one rule of thumb for writing a function is that usually it should be about one page in your editor. If it's more than that, then you should break it down into smaller functions, right, in order to subdivide. That's a good rule of thumb to follow, except here with React functions now, our functional components. It starts at line 54 and it goes to line 421. So this would be an extremely long function, right? You would want to try and break that down into smaller components for sure. You have nested functions that are defined in the namespace of the function, because in classes those would be instance methods. In the functional paradigm, you don't want to pollute your global namespace, so you end up having functions within functions within functions, which is already a little bit weird. And then also this new syntax for defining functions. They seem to really like the idea of using closures, and I understand closures. I programmed in Scheme and Common Lisp for a long time, so I understand closures, but now this is the new syntax. And then you have these hooks, which are called for your functional components. And now the lifetime of this, I really have no idea. Like a function usually, you would expect things, if you have a standard function here, I have low, high, mask, inverted mask, and red as local variables. When do they get allocated? What's the lifetime of these? Well, they should be allocated when you call the function, right? When the function starts, they get allocated. When the function exits, they get destroyed. So, okay, fine. That's sort of what you have to do explicitly here for OpenCV. But with our functional components, I really find it very difficult to figure this out, because you return HTML DOM objects. So here the canvas to select the color and the sliders. And when your function terminates, then these and the reference to it are still live, so they are not deallocated at this point. Also, the state, you have special syntax for dealing with state, which is here to use something as a state. So when exactly does this get allocated and destroyed? It can't be destroyed when the function returns, because the whole HTML that this depends on is still live. So it's not clear to me the lifetime of these things. I think it's pretty obtuse, and I don't see writing a function, writing a class and then calling it a function, why that is any better than just having a class. So this was just some fun experiments with React, because I hadn't written any React code before. So now if you do front-end web development, I mean, it is, as far as software distribution is concerned, it's very cool, right? It runs on anything with a browser. So your iPad, your Android, your iPhone, your Mac, Linux, Windows, whatever they design 5 years from now, I'm pretty sure it'll still run a web browser. So the software distribution is very cool about it, and we want to use it so that for our robots, I don't need to write different clients for different operating systems. I only need to write one, and it can be served from the robot itself. So that's kind of neat. But a lot of frameworks and some pretty opaque reasoning for changing things. Okay, so today I just want to introduce another pretty interesting algorithm it's called seam carving, and we'll see what it does in a second. But most importantly, this particular algorithm I like because it's a very nice example of dynamic programming. And dynamic programming is a very powerful problem-solving strategy that allows you to speed up your computation in lots and lots of different domains. So it's an important algorithm to understand and know how to use, but some of the examples are either too simple or too difficult, whereas this one is sort of just at the right level to be able to understand it. So let's talk about seam carving. And let me try and find a nice picture. So this is Tata, French comic, which is kind of nice. But let me try and see if we find something else. Can take the skyline from Taipei 101. And temple picture. But I don't want the full image, I just take this part. So here we start out with the image of Taipei 101, and I want to be able to make that image smaller, to zoom out. Use it as a thumbnail or something like that for my picture, for my website. And then the problem is when I resize the image to make it smaller, then I lose a lot of the detail, right? Clearly. So here the Taipei 101 building is sort of blurred out. It's just a small component now. Now, what I would like to have is to have an intelligent resize so that the parts of the image that are interesting are maintained, right? So I can still have Taipei 101 at a reasonable resolution, and the parts of the image that are not interesting are removed. So in this case, the idea would be I don't really need that much sky, right? The sky is kind of not interesting. So if I zoom in, I would like to keep the Taipei 101 part in more detail and instead reduce the amount of sky that I have in the image. So we want to focus on interesting parts of the image. So then the question is, if I show you this image and I ask you which parts are interesting, then most of you would agree that the sky is not terribly interesting, but the building is interesting. And as humans, we can do that easily for pictures. Like I can pick some other picture. You're from the UK, right? Then we'll just take a random picture from the UK.
I'm not British, but yeah.
Close enough. So any one of these pictures, if I click on it, then what do you think is the interesting part of this picture? The bridge, right? Most people would say the bridge. Then let's try some other ones. How about this one? Probably that arc there in the ocean, right? The rock formation. Okay, this one a little bit tough. The flowers in the foreground and the rocks. Nope. Actually, I've never seen nice places like that in the UK. I don't know where that will be. Okay, scenery. Let me see, there were the other ones that I wanted to show. One of them was the tree. Where's the one with the tree? In Auckland, here. Yes, I guess that's, yeah, so Auckland in New Zealand has this one tree hill, and it really was quite stunning because when you entered the city, there was the hill and there was exactly one tree on top. So the first time I actually went there, I asked them, what do they call that place with the one tree on top? Then they said One Tree Hill, and then of course, yeah, that's a perfect name for it. That tree was a sacred tree for the Maoris, the natives of New Zealand. Unfortunately, about 20 years ago, some extremists, some demonstrators attacked the tree and cut it down. So it's gone now, and they put a obelisk in that place. I actually forgot about that. But anyway, in this picture too, the interesting thing would be the obelisk, right? Most people would agree. So for us, it's easy to tell which parts of the image are interesting. But if you think about how to do that with a computer program, then what do you suggest? How would you get a computer to understand what it means to be interesting? That is a really, really difficult problem. When you think about it, there's lots of nuances to it. Computer vision researchers have been working on it for 50 years, and we made some progress. However, it's still a very difficult problem. The most modern approach to it in 2023 would probably be to just have 1 million pictures being classified by people and ask them to circle which ones are the interesting parts, and then to train a neural network on it, and then hope for the best when you show it pictures hope for the best when you ask the system to generalize to unseen pictures. So we don't want to go down that particular path. We're looking at a more traditional approach to computer vision, and then see how far that will work, or how well that will work. So one way of talking about interesting, whether a picture is interesting or not, would be to think about the amount of information that is associated with a particular pixel. And then the assumption would be that if the pixel is very different from its neighbors, from the background, then that would be an interesting pixel. And if the pixel is the same as all the neighboring pixels, then it doesn't actually add a lot of information to it, to the scene. So that's basically what modern, what computer vision researchers are trying to do. They came up with ever more complex ways to define this energy in the picture. It's then called saliency in the research literature. But one of the simplest approaches, and one that works surprisingly well, is to just look at the magnitude of the gradient as an indicator for the interestingness of a particular pixel. And the reason why we choose this one is because the gradient, we know how to calculate that very efficiently using convolution masks and Sobel edge detectors. We can easily calculate the gradient in the image. And then other more complex algorithms are usually not applied. They don't depend on just a single pixel or pixel and its neighborhood, but they depend more on the statistics of a particular patch in the image. So then, instead of just looking at the difference, you look at how much difference do I have for this pixel, how much difference does the next one have the next one. And then you can calculate various statistics, try and model these as different types of probability distributions. Then you can see how far out of band or how surprising a particular pixel is by looking at the probability that that pixel would belong into this particular distribution. But as a first attempt to use the magnitude of the gradient is a reasonable first step. And I guess surprisingly it actually works. So we can have a look at our picture size. It's not, I made it a little bit smaller. If you run the code locally, then of course you can use any other kind of image that you want. So this is zoomed in quite a bit. Okay. So here we can calculate the gradient. Here I implement it as just looking at the differences between the pixel and its 8 neighbors. And simply sum up the absolutes of those. So this will be a very slow approach to calculate the gradient. In practice, I don't need to look at all the differences. I can just apply the Sobel edge detector as a convolution mask and then sum up the two convolutions, or actually that would work. Just change that code a little bit. Or I can also calculate the norm of the convolution, so that will be the square root of convolution 1 squared plus convolution 2 squared. Both of those are okay. Let's take this one. Square root. Squared. Yeah, they're all positive. So why the square root? For which value? So let's see what the minimum and the maximum is. Square root should only be not defined or in legal value for if it's negative, but how come the minimum is, okay, so the problem is why do I get an error here for illegal value? Because what I calculate is perfectly, should be correct, right? It's a convolution 1 squared, so that should be a positive number. convolution 2 squared is a positive number. So two positive numbers added together will give me a positive number, right? But when I look at it and ask for the minimum, then it prints out that the minimum is negative 32,326. So the problem is that the convolution 1, convolution 2 are returned as signed 16-bit integers, which have a maximum range from minus 32,768 to 32,767. That's the range of numbers for 16 bits. So here, this is an overflow. Right? The number is actually larger than 32,767. But if I add 1 to it, 32,768 is going to wrap around and it'll be interpreted as minus 1. And so that's why we end up with the negative number here. So if I wanted to fix that, I have to change this to 32-bit integers. Now it doesn't like buffer formats, destination format. Buffer format is 5. 5 is, so how about 32-bit float? Okay, now it's, so now we get the correct numbers here. But I had to swap it to floating point numbers or 32-bit numbers here. This one here requires a larger domain. And then we have our gradient. So now I can take the gradient and normalize it in my image. Then let's see, here would be the output of our gradient image then. We have, and it sort of makes sense, we have very strong gradients along the edges of the building, a little bit for the clouds, and the sky is basically dark. We can see what this is so strong in that this edge here is the most prominent edge. And then this one here against the sky is not so prominent. You can have a look. So this is our image now, our input that we're considering. And now I want to reduce it, right? I want to make the image smaller, which means that now I want to take and carve out a seam, and I can do that based on, we'll consider cutting out a column first. So here's my image. Now I want to start somewhere here and cut out a column without distorting the image too much, and remove that. Then once I have removed the column, now my image has shrunk, right? So that would be, that's how we do the zoom basically. We cut columns out, and then next step we would cut out one row. Now, using this input image, it's clear that if we do cut something out, then here I actually have a lot of choice. Right? Anywhere here, there's no gradient, so I can just remove a column here. But if it's something with the clouds here, for example, then I probably don't want to cut out the cloud. I'd like to cut out a seam that sort of may start here and then goes through like this. So the seam doesn't have to be a vertical line, it just needs to be connected. So from every point, when I start with an image, like this, then I have some parts that have a high gradient, so let's see. Some pattern like that. Now let's say I start at the top and I want to cut out one seam, and if I start here, then anything that I didn't mark in, I assume that it's a low gradient. So this is our first pixel here. So then I have, basically every time, I have three choices, right? I can go to the left, I can go down, or I can go to the right, because I want to remove a continuous seam of the image, not just a horizontal or vertical line. So now, let's say I go to this position here first. Then I go here, then here, 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 here. Right. Now I have a continuous seam that I can cut out of the image. And what I can do is I can calculate now the total energy that I would be removing out of the image. Right? So here, let's say these ones are all 0, but let's say here I have a pixel, and there I have a small gradient of 5, and here I have a small gradient of 7, and here I have 9, and here I have 12. And then I go here, these are all 0. If I now sum them up, then the total energy on this path would be 12, right? 7 plus 5. Now, the goal for this algorithm would be to find a continuous seam that I can carve out, and I want to minimize the energy. Right? So I want to calculate the arcmin of the energy. And that's the seam. Now I have the seam, then I can remove it, right? Then I can cut it out. So that's the algorithm. Now we need to worry about the implementation. So what's the problem with this algorithm? What we see here is at this point I had 3 possible choices, right? Down, up, left, down, and down right. And for that seam, it's clear that the going with the 7 here is the better idea, right? If you just look at this area here. Because if I'm here, whatever I have on top here won't change. But now I either have to pay $12, $7, or $9 to continue. It seems to make sense to use the $7 option, right? But that is only a local decision, and it may not lead to the global minimum, because if I now change this and I get $100, here I have 120, and here I have 90, and here I have 5, then if I choose 7 here, now I can't turn around and go back the other way, right? I have to keep going down. So I either have 7 plus 120, or 7 plus 100, or 7 plus 90. So the best I could do from this point onward would be 97, and then whatever follows here. So the number would be larger than 97. If I would have taken, and here I can make this 19, right? So that it's a much worse choice than the 7. But if I go 19 here and 5, then I end up with 24, which would be much cheaper than going 7 following the 7 here. Right? So this is a global optimization problem, not a... Oh, Ilham, I think it's rebooting here. Oh, now it's back up. Make sure we're still connected. Okay, yep. I think everything okay. So this is a global optimization problem. If I follow the greedy strategy, this would be called the greedy algorithm. If at every choice point you pick the one that minimizes your cost to continue, that's a very simple algorithm to implement. It also runs very fast. Unfortunately, it doesn't give you good results because you will make the locally optimal choice, but it's not guaranteed to give you the globally optimal choice. And this is sort of the core of artificial intelligence problems. Similarly here at the top, right? We followed this path, no idea whether this path here would be any better. So the problem with this algorithm is that I basically have to guess. I have to evaluate all the possibilities. I can't just use the locally best choice, which means I have to, in the worst case, evaluate all the possibilities. And then how many possibilities do I have for this particular algorithm? Now, at the top, assuming that I know my start location, my start column, right? We just ignore the first one. Then here, I have three choices, right? From the first position off. I have three choices. Then, for each one of those, I have another three choices, right? So then, at the second level, I have three squared choices. Then at the third level, each one of those has three possibilities. So that means we get the product of threes, right? 3 times 3 times 3 times 3. And how many of those do I have? Well, I get one level per row. So that would be 3 to the power of h, where h is the height of my image. That is simply the number of leaf nodes that I would have in the tree here. So this is actually just the number of pixels that I have there at the bottom right. It doesn't even include the ones in the top of the image. When you're dealing with this kind of algorithm, usually you only focus on the lower level, on the leaf level, because why do I really only care about the number of nodes that I have in the leaf here at the bottom when you're doing analysis with these kind of algorithms? Well, if I look at let's see how that works out. If I look, the number of leaf levels that I have is 3 to the power of h, right? The ones above that is what? Huh? 3 to the h minus 1. No, that would be the ones that at level h minus 1. So above that I have 3 to the h minus 1 plus 3 to the h minus 2 plus 3 to the h minus 3, so on and so forth. Right? So that would be the sum of I equals 0 to h minus 1, 3 to the power of I. But you can actually prove that by induction. I think the total number would be so I think the sum of this is actually 3 with 1 1, 3. Look that up. For 2, it's actually 2 to the I plus 1, which means that if you have 2 successors, then 50% of the nodes are in the bottom layer, 50% are in all the layers above. So this number here, if it's 2, then the sum I equals 0 to I minus 1, 2 to the I is equal to 2 to the I minus 1. In the bottom layer you have 2 to the I nodes. So that basically means 50% of the nodes are in the bottom. If B is bigger than 2, then I think it's less. So how can we, what would that be? I think it's 3. Oh, maybe I should ask that of ChatGPT, it probably knows. Like 0 to n. So it's a proof by induction. It's 3 to the power of n plus 1 minus 1 divided by 2. So n equals 1. And then it will go to 2. And each one of those, actually, yeah. So this will be 3 over 2. H minus 1 over 2. So, and here we have 3 to the H. So that means that we have 3 to the H over 2. So that means 66% of the nodes are in the leaves, 33% are in the top, roughly. Right. So that means that, and if this base becomes bigger, then it's even more leaves. So for these kind of exponential algorithms, the number of nodes that you have in the leaves are much bigger than the rest of the tree. So usually we only care about the, if you have this as a problem-solving problem for a robot, and you're trying to have a robot that can pick things up and move them around, and it has to build a IKEA table, and it takes 50 steps to do that, and the robot has 100 different actions, then it's going to be impossible because the 100 to the power of 50 is way too large. But even if you were to try and approximate that, the vast majority of the nodes will be in the leaf nodes. Anything above that will be a tiny fraction of the work that we need to do. As counterintuitive as this may sound, but that's the reality of these exponential algorithms. It's a level that really kill your performance. So our problem is, I now have a picture, I have a tiny picture, right? The picture is very small. Right? It's not a very high resolution picture. But it has about 200 rows. So now my algorithm might be looking at a complexity of 3 to the 200, which is, how long will that take to run on an average PC? Three to the 100 is an astronomically large number. There's no way you could possibly run this. Right? 2 to the 100 is the number of electrons, protons, and neutrons in the entire universe. Right? That's what people estimate. 3 to the 200 is super astronomically large than this for each one of the universe. It's like trying to have every electron is its own universe, and you're trying to paint all of those elementary particles billions of times over, right? So 3 to the 200 doesn't sound like much, but it is mind-blowingly large. And it doesn't matter whether you have one computer, 1,000 computers, a million computers, or billions and billions of computers, you're not going to be able to calculate this in the lifespan of billions of universes. So this is completely, the algorithm is theoretically sound, it would work, but it's completely impractical. And if you now think you have a real image, so you have a 4K bitmap and you're trying to apply this, then it is going to be even more fun, right? Because you have 3 to, what's the 4K resolution, 2180 or something, 2160? So 3 to the power of 2000. Yeah, it's an extremely large number. Completely intractable to do that. So what I said at the beginning was that this algorithm is kind of neat because it takes that complexity and ends up with a optimal algorithm that works and runs fast enough to find the optimal solution. And the way that it does that is by using dynamic programming. So, if you have used a SLAM algorithm, for example, then you've already experienced dynamic programming. Pathfinding algorithms, Floyd-Warshall, Dijkstra's algorithm are dynamic programming algorithms. Here I just show the complexity. And these kind of algorithms where you multiply, you don't add, but you keep multiplying the runtime, right, where you have more and more choices per level, they all have this kind of shape. They have this exponential complexity. For 3 to the power of h, this is 1.2 trillion here, 1 to the 10 to the power of 9. So that would be US trillions. So that's already very, very bad complexity here. You may grind through that on a PC in a couple of hours, but that's for level 17, right? So that would be a 17 pixel image, 17 by 17 pixel image, which is not really an image. It's a tiny collection of pixels. The shape of the curve is important because it basically shows that as you run up your runtime is basically doable, not too bad, boom, and then it hits the wall. And it doesn't matter if you have a faster computer, if your solution that you need to find is out here somewhere, right? You're never going to be able to reach that. Even if you now have, instead of one computer, you have a billion computer, you can squash that graph a little bit. But you still have that shape, so out here, there's no hope. And of course, this would be 30 then, right? So 200 would be over there, and 4,000 or 2,000 would be at the other end of NTNU. So you're never going to get over this hump here. So dynamic programming is a clever algorithm that uses caching in order to make these kind of problems tangible and be able to solve these kind of problems. The dynamic programming problems all have certain features. One is that you have a set of reused computations, subproblems. So you have smaller problems that you can efficiently cache the solution for those subproblems. And once you have the subproblems, you can efficiently construct a solution for the original problem using the solutions of the subproblems. Okay. So that's the idea for dynamic programming. So we'll go through and look at an image. So here, this will be a random image that we have. And I want to be able to cut the seam for this particular image. So let's make that 9 maybe. So here's our table. Now, I talked about subproblems. What will be the subproblems that I can actually reuse? For this problem? Well, the subproblems exist or occur because I want to find the minimum path through this image, and the algorithm actually swaps it around, but I'll just do it going downwards. Let's say if I want to find the optimal path, right? Then at this location here, or if I'm at this location here, if I'm now at this point here and I'm considering whether I should go left, down, or to the right, and my choices are 7, 9, 11, then we already said that locally picking the best choice is not going to do me much good, because that greedy algorithm may follow the wrong path, like we would do here. Here, the greedy algorithm is going to give us a non-optimal solution, right? If I want to make the right choice at this position here, then what do I actually need to know? What I actually need to know would be not just the gradient for this pixel, but I would need to know for all of the paths that I can follow from here, which would be all of those, right? In this entire area, what's the minimum path going through there? So if I know this, right? And I know that the best I can do from this pixel would be like this. And I know that this now has a cost of 29, and this one here, slightly offset, would basically be this whole area here. If I know the best pass through there would be 21, and here the best path that I have would be 95, then I know that I should follow 21. Right? And I would simply then follow the best path for this particular pixel. So the first part would be, I can identify subproblems. The subproblems would be to find the optimal path for the subtrees that I have here, the pixels that are below me. That would be a subproblem that I can calculate. Now, when do I reuse them? If I now have the orange numbers, not the blue numbers, not just the ones for the pixels, but the solution for the entire subtree, right? Then, let's say I have here 50, 30, 20, right? Then of course, those numbers are necessary when I decide where to go for this particular pixel here. However, if I decide where to go for this pixel, right, then I need to know this value, and this value. So these two here I can reuse, right? So not only do I need to do the calculation, or if I do the calculation once, I can actually reuse it at least 3 times for the top ones, right? If they're in a layer below that, I can reuse them 9 times, so on and so on. So this is why this particular problem is a good candidate for a dynamic programming solution. We have subproblems that we know we need to calculate. The solutions for the subproblems I can be easily cached, because what information do I need to store with my orange, with my subproblem, with my orange subproblems? The first thing I need to store would be the number of the minimal path, right? But I also need to store the minimal path, because if I just have the number, that I don't know where to go. So I would need to store 2 things, or I need to have access to 2 things. One would be the cost of the minimal path for that subtree, as well as what the actual minimal path is, so that in the end I can follow. Once I have that information, then I can reuse it multiple times, because here each one of them will be reused at least 3 times. And once I have a solution, right, for my subproblems, then I can easily build up the solution for the entire problem. Because what I need to do is, for this point here, if I know 50, 30, 20, then I need to do let's say this pixel here has a local gradient of 5, right? Then, now I know the solution here should be 25, because the minimum pass is going to be this pixel 5 plus following the path for 20. So the minimum solution here is 25. And I need to remember that in order to get to that minimum solution, I need to turn to the right. I need to move to the right. That's all I need. So I can easily take my subproblems and combine them into solutions for the entire problem by simply adding one step in my solution. So then the question is, how do we get the solutions for the subproblems? And in fact, that is now following a 2-step process. First we go down, and then to actually solve the problem, we go up. So first we go down in order to calculate the solutions for the subproblem, our orange numbers. Once I have the table of orange numbers, then I start at the bottom and I go back in order to find the optimal solution. Now this step here with my 4 orange numbers, I don't actually need to store the path here. I can simply do that by following a greedy algorithm. Because if I have the orange numbers, then starting at the bottom, I would pick the minimum number, and then I look at the other numbers that I can go to, and I would follow, in this case, the minimum. If I do a greedy move with the orange numbers, then that's going to be the optimal solution. In this case, I'm not doing any search. I just follow the path backwards. Now, given some images, there may be 2 minimum paths. Right? There may be more than 1 minimum path. They're not unique. In this case, my algorithm will just pick a random one. So first we construct our orange numbers. And then we do a greedy search going upwards. So in order to construct the numbers, here I can estimate different paths, right? So 0, 1, 1, 1, 2, 2. So I go 0, 1, then 1, 1, then 2, 0, then 3, 0, then 4, 0. The only thing that is necessary is that the rows increase by 1 all the time. That consecutively go through the rows, right? So row 0, row 1, row 2, row 3, row 4, and I start at 1 and then go down 1, then I go to the left, then I go down 1, go down 1. If I follow that path, I get 283 for this particular problem here. So 45, 27, 74, 41, 96 gives me 283. And if I start at 3, and then I go 2, and then 2, 2, and then 1 and 1, then I end up with 260, and I can get 211 with this. So these paths are just some examples. Initially, a greedy algorithm, just picking the best possible successor, seems attractive. However, you may fall into a local minimum. Since you make local decisions only, your algorithm may get sidetracked, may make the wrong decision at the top, and then there's no way to undo that or recover from it in any way. So in this case, the local minimum is not good enough, so we need to come up with we need to do something a little bit more clever than just the greedy algorithm. But here would be an implementation of the greedy algorithm where I just look, I go through the image and then I look at the pixels below, to the left, below, and to the right, and then I calculate which one of those has the lowest, and then that's the path that I follow. So if I take that particular sample, then the greedy algorithm would return this solution here. Which is not too bad, it's 136, so it's better than the random ones that I picked here. The best I get by random selection would be 211. That would be another algorithm, but obviously just picking random moves and then hoping to find a solution is usually not very constructive. Unless you have a domain where there is an abundance of solution, that usually never works. So other examples, yeah. Dynamic programming is an optimization technique developed by Richard Bellman. Break the problem down into subproblems, find solutions for the subproblems, cache the solutions for the subproblems, reuse them in solving the larger problem. Now, most often the algorithms are described using as recursive solution strategies. But of course, they can be implemented using loops as well. In this case, we use implementation as loops because it's a little bit easier to understand. The other examples of dynamic programming algorithms would be Dijkstra's algorithm, Floyd-Warshall path planning algorithm, or the Levenshtein distance. Does anybody know what that actually calculates? By any chance? This would be the algorithm for detecting the minimum editing distance. So if you implement a spell checker and you want to make the word that the user typed is not in the dictionary, so you think it's misspelled, right? So then you want to make a proposal. Did you mean, like Google, if I type what can I type? Career. Okay, I'm sure this in Chinese means, did you mean career professor, right? Taiwanese students, what does this actually mean here, the Chinese? What does this mean? I mean the Chinese, can you translate it into English? Search results containing career professor. Usually, what's the other part? This is a question. One search results containing. So usually it asks. So anyway, if you want to make that kind of suggestion, then you need to know how close the words are, so you need to figure out whether two words, how many mistakes the user would have made when typing those. So then you would find, because if somebody mistypes something, if I type doc, and then I have the possible suggestions, then probably you want to suggest dog as opposed to cat, right? Because if I type this and to get dog, I only mistype one character. Here I would have had to mistype all three characters. So then that's what the Levenshtein distance calculates. And it's an efficient algorithm for doing that. In fact, it's very similar to what we're doing here. It also works with a table, but instead of going up, following the minimum path, you follow the minimum editing distance. So here's one example. If our sum so far is 2, 5, and 3, then for this point here, I know that's going to be the value of this point plus 5, and I need to go to the right in order to reach it. So these are the subproblems that I can repeat. So as I go through my rows, that I know that the minimum pass, the minimum energy seen, is going to go through the top neighbor, right? Because now I start at the top and I keep calculating the minimum energy path for one row down. So we go one row, from one row to the top to the bottom. And that's basically all we have to calculate. So there's not that much to do. If I have some numbers, 7, 12, 15, 19, right? That's the top of my image. Then for this pixel here, because that's the beginning of the image, then the cumulative cost of getting from here to the top is, let's say I have some other numbers, 15, 19, 12. The minimum number for this, the cumulative cost of going from here to the top will be the 19 plus the 7. So that gives me 26, and I know I have to go to the left. For this pixel here, the minimum cost should be 24, and I also go to the left. For this guy here, the minimum cost, there's no left neighbor, so I only have a choice between 7 and 12, so that'll be 22. So then I can fill in row number 1. Now I'm looking at row number 2, and I have 0, and 5, and 9. Then here I have a choice between 22 and 26, so I'll pick 22 plus a 5 will give me 27. Here I have a choice between 22, 26 and 24, so I'll take the 22 plus 0 will be 22. And here I have whatever this value is, 17. So in this case I have 9, 17, so that will be 28. So now from these 3 pixels I know this is the minimum value. Because 27, 22, 28. This would be the minimum pass from here. I get to the top and I'll have to pay $22. So this will be the downward step of our scene carving algorithm. We simply calculate the minimum energy path, the global minimum energy path, by looking at the top neighbors from where we could have come from, and then updating the costs. So here's a little animation of the algorithm. Here's the gradient magnitude of the image. And this is what the algorithm actually does. So first we add the first row, and then here I get 46 because it's 3 plus 43. And here are the numbers that I can add up as we go through the algorithm, as we go through row by row. And I have to say so myself, I like that animation of the algorithm. It's pretty cool. So that's our table now filled out. Now if I look at the bottom row, then what do I know? If I look at this row here. That means that the minimum seam through that image is going to be going through this pixel, and it'll cost me $136 to get to the top, because that should be the minimum one. All the other numbers in the bottom row here are more expensive, right? Higher. So this will be the minimum, and that's the minimum cost that I have to pay. Now, if I want to know how to get to the top with this minimum, then of course it's easy to do, because I must have come either from here, from there, or from there, from one of those 3 neighbors above me. So The minimum here was 102, so I must have gone through the 102 branch. So the last step was to go right. From here I went 99, then 64, then 17. So the minimum, now I know the minimum path, the minimum seam will be 17, 64, 99, 102, 150, 102, 136. Now I have marked the pixels, then I can remove those pixels from each row, and that's one column removed then. So then next step, we can either reduce a row or do another column or something. So this is the algorithm for finding the minimum energy seam then. It showed it. I just removed the column. I didn't highlight which one would be removed. But if we look at the image, actually let me print. So in order to figure out which column was removed, there's too many. Then it's a little bit hard to see because all of them are it's in this area here. Strongly suggest guess. So it's just black, so there's more blackness that is removed, so it's hard to see. So we'll show the path. Oh, it actually picked this one. So it avoided the cloud cleverly here, and then just went through the. Here is how it works in the table. If we look at the actual pixel values. usually it would pick the red ones. The path going backwards. And here's another table. See how the algorithm works. We'll calculate. Here we show the greedy path as well as the minimum energy path. The greedy path would be the green one, and the blue one is the minimum energy path on this particular picture, so you can see that they're different. This path here would cut out the cloud, so that doesn't seem like a good choice. Even for a simple image like that, you can see. Once we have the minimum path, then I can just go through the image and remove the pixels that are in the path. Then now I get a new shape for the image, 69 by 82 pixels for the image. Yeah, now I only have, because I did that on a larger pixel before, so you don't need to reduce quite so many. Carve scene. Let's remove 60, so let's remove 5, 8. Remove a couple more. $25. Okay, so now you can see the effect a little bit here, because this one is not really scaling that much. That's why it looks like that. Here, but however, you can see that the cloud and the Taipei 101 actually remained larger. This would be the actual scaling. So let me try and do this, the new width is divided by 2, so iteration would be the maximum of the new height 0.5 times up. And if we do 4, is integer scale times height. Integer scale times width. And the number of iterations that I need to apply would be 1 minus scale, 1 minus scale multiplied by height. And 1 minus scale multiplied by width. And then the integer of the because I only, this one is actually better. It's only because I only carve in the, columns out, so now it's stretched. So if I want to do that, I should rotate. The easiest way to do that, of course, it will be, I could implement 2 different algorithms, one for removing a column, the other one for removing a row, but that's kind of wasted, I guess. I would want to just rotate the image by 90 degrees and then extract the column. That's the same thing as removing a row. So I can implement that. I need to so our image is equal to np.rot. I forgot about the arguments. Or is it just actually I don't need to I can just transpose the image, right? So that is this image t. Then we'll carve the seam, which now is just supposed to rotate the just to remove the rows, and then here's my S image, and that will be our image transpose. should end up with 62 by 43, 42, 62. So why is this 100? Here. Resize. Okay. Okay. New width, new height is calculated on top. So here we carve the seam, and then here this would be image dot zero. Image dot shape 1. And I want to shrink it to 50%. So before I only did it in the column, now I extended the program to also do the rows, so we get a little bit better idea. And we end up with a pixel eventually 84 by 124. So this is a scaled one. So here we have 200, 180, 120. Original image, the seamed carved image, and then resizing the original image. That should be width and height. And there you have it. So here would be our seam carved image. Here's our original image resized. And you can see it actually does a lot better job. Right? The interesting parts of the image, the Taipei 101 is certainly still in there. What is this? 180 to 120. But the original image is 200. I'm not scaling them to the exact. 208, 248. So 208 should be 104, 120 after scaling. I'm sure I have width. No, resize should be width and height. Width, yeah. New width and height. New width, new height. Where is it not 102? One 124, yes, and then 124. I start with 208. Then after I'm done, I get 85. There should be one. Not sure why, but it should be 102 there. So the size is slightly off, which is why it's scaled in this direction. But anyway, this is our scaled, our seam carved image. Most of the features, certainly the Type A 101, remains a lot more visible than in this particular picture. It's not quite right. No. This is scaled A1, so here's the new image. And then maximum of that. Here's the resized image. So this is a rotated image. Because of the aspect ratio, that's why it looks because if I rotate, so it's a 4:3 image state. So we end up with 84:124, 124:84. Okay. Removes 40 pixels. Yeah. And so again here zoomed in on the Type A 101. Also when we remove the rolls, and here we still have a zoomed in version of this picture. So the right side is just rescaled. This is our intelligent seam card. So now this algorithm we can use we can make several extensions to this algorithm. One thing that you may have noticed is that when I actually call the carve seam function, I call it in a loop each time to remove one column or one row. Right? Now, if I want to scale an image and I have to remove 100 columns, if I have 200 by 200, I want to reduce it to size 100 by 100, then of course it seems silly that I have to reconstruct this table 100 times. Right? However, it is in most cases impossible to use that table in order to remove multiple columns. And the reason for that is because if I have some path through the image and I remove it, so then this orange path here is gone. If I now look for the minimum, for the other minimum, right, and then start cutting that path, let's say I have 100 here and I have 102 here, right? And those are the two minimum numbers. Then first I would remove this path. Then I start at 102 and I start removing the path. And then so far everything is going well, but now I end up in the same pixel. So then I would have to remove the same pixel twice, which is not possible. Right? So the minimum seam energy path, the minimum energy path, the seam, has to be recalculated after we remove one row or one column. If under certain conditions you could do it, we could do it without recalculating the path if it looks like this. If it wouldn't go here, but if the second path would follow here, then it's actually okay. Then I could just remove both paths by calculating the table once. But in general, that is not what happens. The paths are often crossed. And if they cross, then that means that you will have removed, you want to try and remove the same pixel twice, and that's not going to work. The other nice thing about that algorithm is that you can actually use it to remove unwanted artifacts from an image as well, because I can use the same idea and exactly the same algorithm. And let's say I have something in the image I don't like. What could we look for? A wall. Let's say you have this picture here with the, I guess they were taking the wedding photos, right? In this picture here, they were taking the wedding photos, but the two deer came and are in the picture now. So that's not going to make your wife happy, I'm sure. But knowing now what you know about computer vision, you can easily deal with that problem because you can force the algorithm to follow a particular path when you're trying to remove things by overriding the gradient image. Right now, our energy is calculated by the gradient in the image. But if I set the gradient here to 0, then that means the algorithm is much more likely to remove the pixels with the deer that belong to the deer as opposed to the other pixels. So if I wanted to get rid of the deer, I would calculate the Sobel edge mask and then simply override this with zeros. And then run my seam carving algorithm. In that case, it's going to start removing the deers. Okay, good. So that's it for today. That's our example of dynamic programming, a very nice algorithm, and also some intelligent manipulation of images. This function now is actually implemented exactly like that in Photoshop and some of the other. So if they tell you they have intelligent cut for removing artifacts, then this is the algorithm that they usually implement. Nowadays they have more complex ones, some of them based on neural networks, but if it runs very quickly, then this is the algorithm that is actually implemented. Or sometimes it's also called an intelligent zoom function. Okay, good. Then that's it for today. Now, next week we will have regular class. The week after that we will have the midterm. Okay, so 2 weeks from now we have the midterm, which will be open book and open internet. And I'll ask you to write several programs similar to the ones that I'm writing in class here.